We're going to bake a cake, and here's our ingredients. We need 2 flour, 3 eggs, and 4 sugar. All right, cups or tablespoons, or I don't know, I don't cook. But those are the ingredients to make a delicious birthday cake. And then I'm going to give you some ingredients on a tray for you to make some cake or cakes with. No one speaks, just answer privately in your head. What if I gave you 4 flour, 6 eggs, and 8 sugar? My question is, how many cakes can you make with the data outside of this circle? Come up with a number. How many cakes? You can make 2. I gave you twice as much of each item that you need, so we've got enough to make 2 delicious cakes. This reaction would run twice. All right, this reaction kind of has a 2 to 3 to 4 ratio. All right, so if that's the amount of reactant I gave you, we'd make 2 fantastic cakes. Let's do it again. Thanks. I'm going to change the tray up. I'm going to give you a slightly larger tray. I'm going to give you 4,000 flowers because it's almost Valentine's Day. Flowers. No. 6,000 eggs and 8 sugars. I want to know how many cakes can I make now. Don't speak. How many? Still 2. I can still only make 2 cakes. In a reaction, this is always the case. One of the reactants will get used up first. When you were messing with Skittles, it happened. In this case, we'll use 4 sugars to make 1 cake, and then 2 of those and 3 of those. 4 more sugars to make a second cake, 2 of those and 3 of those. And then we've got so much, we're drowning in flour and eggs. We have so much in what we call excess, just extra lying over that doesn't get used. But this guy right here that got used up first and made it so we could not make more cake, he limited us. He was our limiting reactant. In a reaction, a limiting reactant is A, the reactant that's used up first, we run out of it first, it's one way to look at it, or B, it's the reactant that makes the reaction stop happening because we no longer have the stuff we need to make it go, even though we might have plenty of the other stuff. And I'll show you how we'll find the limiting reactant just on one of the basic problems that we always do. For those of you working at home, this is the first reaction that we'll be doing. You can pause the video to get the information written down. If you take a look at the back of your cheat sheet, there's a section called How Do I Find the Limiting Reactant? If you skip the bold part that actually gives you the steps that I'm about to go through, it reminds you, it says the limiting reactant is the reactant that causes a reaction to stop because it's used up first. The excess reactant is whichever reactant is not the limiting reactant. And here's the first example that we'll look at. Now, if you look at the question, it says 10 moles of barium chloride react with 9 moles of potassium sulfate. Find the limiting reactant. I can very easily label what that's referring to. It says 10 moles of barium chloride. My barium chloride is here. It says 10 moles. It's a dead green marker. Come on. It says 10 moles of this guy are reacting with 9 moles of potassium sulfate. 9 moles of this guy. I've got 9 flours and 10 sugars. Which one's going to quit making cake first? Is what it's asking. You got to run 2 grids. We need to run a grid with this as my given, and then run a different grid with that as my given. That's what the grids won't have in common. 2 different sets of given information. What the grids must have in common is the unknown. And here's what I mean. Here's my first bit of given info. 9 moles of K2SO4. We need to pick one of the products to be the unknown. It actually doesn't matter which one you pick, but you have to pick the same unknown for both of them. So pick one. Which one do y'all want to look at? KCl or BaSO4? Yeah. All right, KCl, he said. We're going to make this the unknown. Again, it doesn't matter which one. And now we're ready to set up a grid. Now listen closely to this. I've got given units. I've got an entire expression here. There's a number, a unit, and a compound, like we always have. Over here, I don't, though. I just have an unknown and a compound. I don't have a moles or a grams. If the problem doesn't tell you what this has to be, then go to moles. Because for those of y'all that are familiar with your grids, you know that problems that go to moles are shorter than problems that go to grams. But if you run into a problem that says they want an answer expressed in grams, then you have to go in grams. But this right here says nothing about what this unit has to be. So let's go to moles. Two grids. Let's do this one first. All right. It's going to be a mole to mole problem. Look at your cheat sheet. Find the mole to mole grid, and let's draw it. It's the shortest grid, which is nice. It just looks like that. I know that in my grids, I want to put the MOLs and Gs first. So, MOL, MOL, and MOL. The moles to moles grid has no gram squares. Then we go and we put in compounds. If you look at your cheat sheet, these two squares want the given compound. We are analyzing this guy right now. So the given compound is K2SO4. And then this square requests the unknown compound. The unknown compound, we decided we were going to do KCl. All we're missing now is numbers. Follow your cheat sheet. It says the given number is going to be 9. Here it wants the coefficient of KCl, which is a 2. In my single bottom square, it also wants a coefficient of K2SO4, which is a 1. Multiply across the top and divide by the bottom. 9 times 2 is 18. divided by 1 is 18. So look what we have. We've got a theoretical yield. All right, this one gave me 18 moles of KCl. All right, filling in the question mark. Here's what that tells us. Look, look, look. This says that this 9 moles of him is capable of making 18 cakes. He can make 18 cakes. Let's see how many cakes the other guy can make. So set up another grid. It'll still be moles to moles, except now this guy's my given, and we'll use the same unknown so that our theoretical yields are comparable to one another. Moles to moles, which means the grids, the good part is, the second grid's easier to set up. It's got a lot of similarities to the first one that you did. We need compounds. Now the given compound's different. All right? We're using different given information. Now it's BaCl2. So be careful. Realize that you're analyzing a different reactant. However, the unknown square will be identical. You're going to analyze the exact same unknown. So not only will it be the exact same compound there, but all the unknown squares will repeat themselves. Enter numbers. The given number for BaCl2 was 10. The coefficient for KCl hasn't changed. It's still 2. You can re-verify that. And on the bottom, here's where something could be different. The coefficient of BaCl2, well, it turns out that it is the same in this case. Ten times 2 is 20, divided by 1 is 1. Now, we've got two answers. This reactant is capable of making 20 cakes. This reactant is capable of making 18 cakes. Here's a couple of the ways you could look at this question. First off, how many cakes will this reaction make? 18, the smaller number. All right, if one of the reactants is present enough to make 18, the other one's present enough to make 20, then it doesn't matter about that 20. We can only make the lowest possible. Think back to the actual cake analogy from the beginning. So how many cakes can be made? Well, 18. Pick the smaller number. But that's not what this question asks. This question asks, what's the limiting reactant? What's the limiting reactant? There he is. The reactant that gave you that smallest number. So to recap, I know that might have been twisty for a couple of y'all, but all we did was we agreed that we're going to run 2 grids, 1 for each reactant. There was a step where we picked whichever product we wanted to, but we use that product in both grids. The givens will be different for the 2 grids. The unknown will be the same. Let's do another one. Here's our next problem. Here's our balanced reaction. It says pentane reacts with oxygen, with 8 oxygens to produce 5 carbon dioxides and 6 waters. This is called combustion. Anyway, if you look at our problem, gives us some information. So let's check that out. It says we've got 294.4 grams of heme. 294.4 grams of this guy. All right? And 238.7 grams of this guy. So there's our amount of sugar and our amount of eggs. It wants to know which one is the limiting reactant, but you'll notice this one says in grams. Remember, in the last example, it didn't say we had to convert to a certain unit. So you could have chose grams for the other one if you really like doing more work, but I choose moles if no one's telling me what to do. This problem wants us to go to grams, though. So, hey, what's the next thing we do? Look at those products. What's the next thing I should do? Choose one. It doesn't matter which one. Sometimes you'll get freaked out by that part because you think, well, I don't know which one to do. All right, you're going to get different numbers depending on which one you pick. But whichever one of these guys is going to produce less product will stay the same. That's the whole point. We want to know which one makes less cake. We can call either of these guys the cake. One of them, the one that's going to produce less of that one, will also produce less of that one. So who do y'all want to do? Carbon dioxide or water? You got to pick last time. Carbon dioxide. We're going to make this guy the unknown then. All right, he's our question mark. I would love to go to moles, but this problem says that we need to go to grams. So these grids will be what to what? Gram to gram. All right, so go look at your awful gram to gram grid. I'm just going to, you know what I'm going to do? I'm going to draw both grids. Some students like to do that. We're going to have to do two grids anyway. All right, so there's one gram to gram. Here's another gram to gram. The G's and the MOLs come first. This is stupidly repetitive, right? It's just more stoichiometry. So I'm going to copy my cheat sheet carefully and put those in the right place. All right. Remember, these two grids are the same in regard to what we have so far, both gram to gram. All right, so we'll just call this our first given. All right, so if you look at your grams to grams grid, there's 4 squares that require a given compound. So we'll say C5H12 for this guy. C5H12 in all of the given squares. And then here's my unknown squares. We chose carbon dioxide to be the unknown for both grids. Remember, we're not going to change the unknown. Go back and put in values. All right, so let's tackle the rest of this first grid, even though we have that awful second guy waiting for us. Follow your cheat sheet. It says given number. Well, that's 238.7. All right, we're analyzing this guy right now. Going straight across the top, that's a 1 on your cheat sheet. This says coefficient of CO2 is a 5. This says periodic table of CO2. We can do that. CO2 is made up of carbon and oxygen. There's 1 carbon and 2 oxygens. Carbon on the periodic table has a mass right over 12. Oxygen a mass right under 16. There's only 1 carbon, but the 2 oxygens are going to multiply to 31.998. We're just finding a molar mass here. That'll be 44.009. Stop me if I do anything funky. So I found my PT of CO2. Down to the bottom, it says PT again, this time of 5 carbons and 12 hydrogens. All right? Well, do your molar mass. Carbon on the periodic table is 12.011. So I want 5 of those. Plus hydrogen on the table is 1.008. And we need 12 of those. 12 times 5 and 5 times 12 and 12 times 1 all added together. C5H12 has a molar mass of 72.151. But that's from last unit. You should still be efficient at that. Moving to this guy, coefficient of C5H12 is a 1. And then our grid asks for a 1 in that square as well. Now, we can solve that grid and get a theoretical yield for the C5H12, and we will in a moment. But I want to draw your attention to the other grid real quick. Look here, look here. I know you're working. Some of you are working ahead of me. I'm proud of you. But answer this question. What is the similarity in this grid? What will be the same in the second grid? The unknown. The unknown has to be the same. There are 3 unknown squares. So all the information on carbon dioxide will be the exact same. What will be different on my other grid? The given. We're going to look at this guy. We don't even care about him in the other one. All we care about is the O2 in the other grid. I want you to get as far into this problem without me as you can. You too. Pause. Running the numbers in the top grid. 238.7 times 1 times 5 times 44.009 is going to give you a big number when you're just running the top. I get a top value of 52,524.74, which would be fine to write down. You could write down that big old number. All right, point whatever. And we're going to divide that, though, by 72.151 times 1 times 1. All right, so that's what we want in our calculator. And then it will give us a more reasonable number to work with. When I divide the top product by the bottom product, the grid gives me an answer of 727.98. So we know there how many cakes C5H12 can make. But I've got this bottom grid that I still need to fill in. So going straight across with numbers, this wants the given of O2, which was 294.4. This wants the number 1. This wants the coefficient of CO2. Now, you can either trust yourself or not. I'm telling you that the unknown squares in both grids will be completely identical to each other. The coefficient of CO2 is still 5. The molar mass, the PT of CO2, is still 44.009. None of that can change. But you can re-verify if you don't feel comfortable. On the bottom, the PT of 2 oxygens. 1 oxygen is 15.999. 2 oxygens is 31.998 from the periodic table. This wants the coefficient of O2, which is an 8. And then this one, just like that one, is still a 1 in one of my unknown squares. Any questions on my work? Multiply across the top. 294.4 times 1 times 5 times 44.009, again, a very large number. 64,000 and change up top. But we want to divide that by 31.998 times 8 times 1. So do it properly. And when I divide the top by the bottom, I get 253.07. Two different ways I can ask the next question. I know what the screen asks, but let me ask the other one first. How many cakes can we make? 253.07. Always the smaller number. But more importantly, what is the limiting reactant? This guy right here. He is my limiting reactant. Now understand this. Listen to this next thing. Here's what some of you creative students like to do. Your brain associates limiting reactant as being the smaller number. So you'll look at the two numbers that I give you from the very beginning, 15 minutes ago before we started this problem, and you'll just say, hey, there's less of him. He must be the limiting reactant. Do you see why that is not something you can do? Not only did this guy make less, but he made like way less, like more than half his feed. So you cannot drag any information from those starting numbers.